Hello students, in this session we will be mathematically verifying the mirror formula as well as the formula for the linear magnification in case of concave mirror when the image is virtual. In the previous session we have discussed the mirror formula when the image was real, but in this case we will prove the mirror formula and the expression for linear magnification when the image is virtual, right? So we'll proceed in a similar manner. So this is a concave mirror. Again, as you are aware, it's a part of a hollow sphere. It's a part of a hollow sphere. The center of that sphere is known as the center of curvature. And concave mirror means the reflecting surface will lie towards the center of which it forms a part, right? And the center of the spherical mirror is known as the pole. This is the pole. Line joining P and C, that's principal axis. Exactly the midpoint, that is principal focus. You all are aware of these terms. The distance between P and F, that's focal length. The distance between P and C, that's radius of curvature. Now look, image is virtual and we are taking the case of concave mirror. For concave mirror, the nature of image is always real and inverted except one case, and that exception is when the object is placed between pole and focus. It is then the nature of the image obtained is virtual, right? So what to do is, suppose this is the object placed over here. This is the object. This is the object placed over here, A, and it is placed between pole and the focus. Let's draw the ray diagram for its image formation. A ray parallel to the principal axis. After reflection, it will pass through the focus. This is it. We are all aware of it. This is the first rule we have discussed, right? And there are so many rules. One of the rules is a ray incident at the pole will bounce back into the same medium, obeying the laws of reflection. So this is the angle of incidence. This will be the angle of reflection. And obviously, as per the first law of reflection, angle of incidence must be exactly equal to the angle of reflection. Now, these two reflected rays will never meet. The gap between them will keep on increasing. So, if we produce it in the backward direction, let us produce it in the backward direction. So, let's see where the image is obtained. Obviously, it should be obtained behind the mirror. So, it's like this. Produce it in the backward direction. And behind the mirror, it should be represented by dotted lines. These are the imaginary lines. So it will appear as if these two reflected rays are coming from a point somewhere over here. So here the image is formed. So it is formed, the image is formed behind the mirror. So nature of the image is virtual. And obviously it is erect. This is the object and this is the huge image which is erect. So what is nature? Virtual. Image is virtual and erect. Image is formed behind the mirror. Image is magnified, that is the size of the image is greater than the size of the object. So it is only in this position where the object is placed between pole and the focus that the nature of the image formed would be virtual. It would be formed behind the mirror. Right? So let's derive this mirror formula in this case. Right? So what we have done in the previous session was we have considered two equations considering two pair of triangles. We have proved those triangles to be similar and their corresponding sides were taken to be proportional. So that is what we will do in this particular article as well. So let's consider two pair of triangles. We have considered this to be point C in the previous section also. Let us consider this to be point C. So if you drop a perpendicular over here, this is N, suppose. So this aperture is small. So N and P are vanishingly close to each other. So points N and P may be considered to be coincident, right? Okay, let's consider two pair of triangles. What to do is, consider this triangle, this one, the bigger one, this triangle. That is, consider triangle A', F, B'. Look, this one, A', F, B'. I'm considering this particular triangle, right? And consider this triangle, this one, the smaller one. Triangle CFN or P, it's the same thing. CFP. Again I'm repeating, consider these two triangles. Triangles must be chosen very, very judiciously, right? So consider these two triangles, A dash, F, B dash, this bigger one and the smaller one, CFP. Both these triangles are similar. Why? Because this is 90 degree, this is also 90 degree, and this is the common angle, this is the common angle. We are considering these two triangles, this one and the smaller one. This is the common angle and this is 90 degree, this is 90 degree. So again, by A corollary, these two triangles are similar. Therefore, their corresponding sides must be proportional. That is A dash, B dash. What will be its corresponding side? CN, which is equal to CN, which is equal to AB. Isn't it? A dash, B dash divided by CN. CN is equal to AB. The upper distance between two parallel lines is constant, right? Is equal to, now consider the base, B dash F. B dash F. And what about the base of the smaller triangle? PF. Put this as equation number 1, right? Now we have to choose other pair of triangles as well, right? For that, what to do is, consider these two triangles, this one and this one. I am shading it so that you are easily able to identify the triangles which I am considering. Now look, this angle is equal to this angle, vertically opposite angle. This is 90 degree, this is also 90 degree. So again, if these two triangles are considered, these two angles each is 90 degree, these two angles each is equal to theta. So by A corollary, again these two triangles are similar. That is, triangle A dash PB dash, this is P, is similar to triangle APB. Therefore, the corresponding sides are proportional. So A dash B dash, the corresponding side of A dash B dash in the other triangle is AB, is equal to, consider the base, PB dash, P should be the initial letter wherever feasible, PB dash divided by PB. Now here, the point to be noted is that the terms in the left hand side of these two equations must be same. It is A dash B dash by AB, here also it is A dash B dash by AB. So that we can equate the terms in the right hand side of these two equations, right? So from 1 and 2 we get you can equate these two. B dash F divided by PF is equal to PB dash divided by P. Now students, you remember all the distances are to be measured from the pole of the mirror. So P must be the initial letter. So no issues in these three terms. But B dash F needs to be changed. Now look, this is B dash F. This is B dash F. So B dash F, this distance may be written as PB dash plus PF. Right? So B dash F is this distance. This is B dash and this is F. So B dash F may be written as PB dash plus PF in terms of P. So B dash F may be written as PB dash plus PF. Now since all the terms are having initial letter P, so now there won't be any difficulty in applying this sign convention. So using sign convention, what you get is, using sign convention, PF, incident ray is traveling along this direction, PF is measured in the opposite direction, and you are aware the focal length of a concave mirror is always negative. So it is minus F. PB, object distance. Object is real. So for mirror, real object, its distance is always negative. PB dash. Now look, this is virtual object. And the distance of the virtual image is always positive. Why? Because the incident ray is traveling from left to right. PB dash, it is again measured from left to right. So both are measured along the same direction. So it is positive plus P. The image being virtual. For real image, the distance of the image is to be taken as negative. For virtual image, in case of mirror, it is to be taken as positive. So let's substitute these values over here. PB dash, that is V. PF, that is minus F. PB dash V minus V. We can easily solve it. So cross multiplying we get, right? So what you get is, it can be rearranged in this manner as well. Take this term UV from left hand side to right hand side. The sign will get changed. Isn't it? So we get UF plus VF is equal to U. Now divide throughout by UVF. Let's divide throughout by UVF. Both the sides. So we will be left with 1 by V. Here we will be left with 1 by U. And here we will be left with 1 by F. So that's mirror formula for you. So this is how you can verify the relationship in U, V and F. So students, in the previous article and in this article, what we have proved, or rather what we have concluded is, it is immaterial, it is of no consequence whether the nature of the image is real or virtual. This formula holds valid for every nature of the image, right? Let's derive this particular equation as well, right? Linear magnification. Consider this equation. Consider equation 1. So what to do is A dash B dash divided by AB is equal to B dash F divided by PF. Okay. Or rather, you can consider equation 2. Here, if you consider equation 1, there will be an additional 2-3 steps. So what to do is, let's consider equation 2. We can directly obtain this particular formula, right? So instead of considering equation 1, let's consider equation 2 and simplify our result. So instead of considering equation 1, let's consider equation 2. Because already the initial letter P is given. If you consider equation 1, then this term needs to be changed, right? So let's consider second equation. So from equation 2, what we get is A dash B dash divided by AB is equal to PB dash divided by P. Students, we are considering equation 2 because we need not to change anything. We need not to change any term. In case we have considered equation 1, this term would have been to be changed, right? Each letter, each term, it should have a starting letter P. All the distance have been measured from the pole. So, A dash B dash. Let's make use of the sign convention directly. A dash B dash. This is the size of the image and it's erect. So it is plus H2. H2, as I have stated, it's the notation used to indicate the size of the image. Plus, because the image over here is erect. What about AB? Object is to be always placed erect in front of the mirror. So it is plus H1. It's the size of the object. PB, object distance, it is always negative. Incident ray traveling along this direction. PB, measured in the opposite direction. So it is minus U. PB dash, again, it's virtual image. So it is positive. So if you substitute these values over here, what you get is H2 by H1 is equal to PB dash, it is V minus U. And we are aware, linear magnification is defined as the ratio of the size of the image to the size of the object. And from this we get minus V by U. So this is the mathematical derivation of the linear magnification in case of a concave mirror when the image obtained is virtual, right? So that's the relationship between these two. I hope students you have easily understood this particular topic. So last case left is that of a convex mirror. Now look, in the case of a convex mirror also, the same formula holds valid. I've told you the mirror formula, the formula for the linear magnification, whether the mirror is concave or convex, the formula remains the same. And also for convex mirror, the nature of the image is always virtual, erect and diminished in size, right? So let's verify the formula, mirror formula for convex mirror. This is case 3. And the nature of the image would be always virtual, right? So let's move it. This is the convex mirror. It's a part of a hollow sphere, the center of which will lie over here. This is pole, line joining P and C. That will be the principal axis, right? And the center between P and C, that's the principal focus, right? So, suppose ray is incident over here. This is the incident ray which is parallel to the principal axis, right? And this is the object over here. This is the object. This is AB. Object is to be placed in front of the convex mirror, right? So a ray parallel to the principal axis, after reflection, it will appear as if it is coming from the focus. So diagram would be somewhat like this. And second is, if you incident a ray, incident ray at the pole, it will bounce back into the same medium. This is the angle of incidence, this will be the angle of reflection. So these two rays will obviously never intersect. So if you produce it in the backward direction, here the virtual image will be obtained. So this is the virtual image where it is obtained. Drop a perpendicular to the principal axis. This will be A dash, this will be B dash, right? So the intersection of the dotted lines, imaginary lines, will give virtual image. The intersection of the dark lines, real lines, that will give us real image. That's another thing to be noted down. So what about the nature of the image? It is formed behind the mirror. So it is virtual. It is erect. As you can see, the size of the image is less than the size of the object. So the image is diminished. Its linear magnification is less than 1. So let's try to verify mirror formula and for convex mirror. Again, we will follow the same procedure as was done in the previous 2 articles, right? We will consider pair of triangles, 2 triangles. So what we do is, we can consider this to be point C and drop a perpendicular. This may be considered point N, and as I told you time and again, this point N lies vanishingly close to point P. So as a result, these 2 points P and N may be considered to be coincident. These 2 points P and N may be considered to be coincident, right? So let's choose 2 pair of triangles. So what we do is, we consider these 2 triangles. Look, triangle CFP and consider triangle A-FB'. Look, we are considering triangle CFP, this triangle, CFP, this triangle, and this triangle, A-FB'. Now this is the common angle, isn't it? This is the common angle. We are considering these 2 triangles. So this is the common angle, and this is 90 degree, this is also 90 degree. So these two triangles are similar. Therefore, their corresponding sides must be proportional. Accordingly, we can write A-B', A-B', the corresponding side would be CP or CN, and CP, it will be equal to AB, right? A-B' divided by this, and this side would be equal to this AB. So that is what I have written, CP is equal to AB, and B''F, we are considering the base, and the corresponding side of this bigger triangle would be PF. So put this as equation number 1. Right? Now consider triangle, another pair of triangles to be considered. So consider this triangle, this one, I'll shade it for you. Consider this triangle and this one. Look, this angle is equal to this angle. Both are vertically opposite angle. This is 90 degree, this is 90 degree. So these two triangles are also similar. that is triangle APB, is similar to triangle A-PB'. Therefore, the corresponding sides must be proportional, and while writing the corresponding sides, ensure that the left hand side should be same of both the equations, right? So, these two triangles are similar, the shaded ones. Therefore, A-B', corresponding side is AB. It is equal to, consider the base, PB' divided by PB. Base is PB. Fine. Now, as you can notice, the left hand side of these two equations are same. Therefore, we can equate the right hand side of these two equations. So, from 1 and 2, we get PB' divided by PB is equal to B'(F) divided by PF. Again, this term needs to be changed. Every term should contain P as the initial letter, isn't it? All the distances are to be measured from the pole of the mirror. So, B'(F), look over here, B'(F). So, it can be written as PF minus PB'. This is B'(F), it may be written as PF minus PB'. So, let's do it. PB' divided by PB is equal to B'(F) may be written as PF minus PB' divided by PF. Now, let's make use of sign convention. Let's make use of sign convention. Okay. PB. Object distance, it is always negative. PB'. Image formed as virtual. Now look, PB'. It is measured along the direction of the incident ray. It has to be positive. PF. Focal length. PF. Again, it is measured along the direction of the incident ray. And students, do remember, the focal length of a convex mirror is always positive, right? So it is plus F. Substitute these values over here. So what do you get? V over PB is minus U. It's equal to PF, it's plus F. PB', it's plus V. PF again F. Let's cross multiply it. So we will get this term. So we can rewrite the above equation like this. And lastly, if you divide throughout by UVF, as we have done in the previous two articles as well, what do we get? 1 by U plus 1 by V is equal to 1 by F. And that's the mirror formula for convex mirror as well. Right? So the formula remains same. It is immaterial or it is of no consequence whether the mirror under consideration is of converging nature or diverging nature. This formula holds valid for each and every type of mirror. Right? So we can derive this formula as well. Let's consider equation 2. Right? No need to change any term, that's why I'm considering equation 2. So from equation 2, what we get is A dash B dash divided by AB is equal to PB dash divided by PB. You can directly make use of the sign convention over here. A dash B dash is the size of the image and it is erect. So plus H2. Plus sign signifies that the image is erect. AB, object is always placed erect. So it is plus H1. H1 is the notation which we are using to denote the size of the object. PB dash, we are aware, PB dash, it is plus V. PB, we are aware, it's minus U. So let's substitute the value over here. So it is H2 by H1. PB dash is V. PB, it's minus U. So linear magnification by definition is equal to the ratio of the size of the image to the size of the object, which in turn is equal to minus V by U. So that's the formula. Clear? So these mathematical expressions, if possible, try to practice. Then only you will be able to appreciate certain numericals which are based on these ray diagram and these mathematical formulas. Right? We'll continue in the next session.